Okay, this UniCourse video, we're looking at instrumentation and control systems, and we will be looking at the learning outcome 3 hints and tips. And this is the actual criteria which you can have a look through. I'm looking at the terminology, the concepts, look a bit on feedback loops, open and closed, system tuning techniques, including Ziegler, Nicholas and Cohen. And I'll go through this through a mixture of slides, of diagrams, and we're looking at the next presentation, which will be on simulation. So first thing we need to look at is the distance velocity lag. Basically what we want to try and do is make sure that the equipment that we are working with in a real life situation is working in a very stable manner. So it's important that when we set the control side, which is the inputs and the outputs to the motors and the devices which set the heat and temperature and things like that, anything which is driving things, they're all stabilized and they're set at what the operative wants them to be working at. And here we'll have a graph showing the temperature, and we can see what the set point looks like, and we can also see what the current value is, and then we just want to make sure that things are running in a very maintained way under the time that we have to use it. So this is a distant velocity lag, and that's just a typical example. So when we're using things like a boiler, which is a good example, of course we switch the thermostat on. Now the heating system has to get up to a certain level, and that has to be maintained while the equipment is running. So this is how it all works. So we set the temperature, and then the thermostat will control it, and there'll be various feedbacks back to the set point. And we can see the graph here, how it's demonstrating. This is known as distance velocity lag graph here. Now we're looking at the capacity. So what the limitations of the system, how much quantity the system can hold, and that can be something like a silo or something where it's holding liquid. It can be devices where they have to have an optimum amount for the system to work. Now this is where we're looking at fluids. We have a container, possibly like a silo or a weighing machine, so we can operate it. And the way the amount we have is simple, like a charge and a capacitor which can hold. Now with systems like this, we can have some problematic issues. For example, the electronics could fail. We could have the spillage, or in some systems, in a system where they have to be kept certain temperature or in an ideal environment, in a pressurized place, there could be an explosion, and these are things that mustn't happen. So this is why we have to monitor and make sure the systems are running correctly. Now the other thing we see as well is the resistance that can actually occur. We find that no system is 100% efficient. We have to make it 99.999%, and we find that we do get some form of resistance. Now this could be the wear and tear of equipment or any other issues that come into it. So we will have to do some various calculations, and we'll be getting into what is known as the algorithms to work out so that we don't lose anything, that things are working correctly and efficiently. Now sometimes it's not always easy to take an account of it, and the small resistances which could be in sort of in the micro, nano and stuff like that, they may not be able to be seen, but they have to make some allowances because these could affect the control the systems running. And of course, if you've got parts of the systems where you will have some form of resistance, this can add up, creating a more of an issue on how the system is running. Now, in most, and I would say most in here in the UK, what we'll have is we'll have a safety factor, and that has to be employed so it overlooks for anything, which includes in the compensator side of the system. Now, we look at gain in one way. That is something where you put something into an input and you get a greater output. Now, we have things in the control side of things as known as static and dynamic gain. So what's static gain? This is where the gain of a system, so it could be unitary, it could be just the amount in, there's no difference, but it remains constant. In other words, the output stays the same as the input. And this is referred to on a steady state. So this is where these systems are running, that the controllers that control them and the loops, the output, the sensors are maintaining the gain, which is a level playing field. It's running and not moving, going up or not going down. Now the dynamic gain is slightly different. This is adapting to the variations of the input. Now you can sort of say with this part of it, this is where the feedbacks will come into it. So if we want to keep the system running at a certain speed, a certain temperature, a certain pressure, and there is some variance within the system, either resistance or something else, then we have to make sure that the system can then change and adapt to the variations of the input. So this is where we may have an input which may slightly change, but we need to keep the output very much at a sort of certain level. So of course what we're saying, the static gain and the dynamic gain will not be a constant value, and it depends of course on the time. So that's what the dynamic gain is. It's not so restricted, and it's unable to make sure it keeps that it is stable. Now stability. Now when we look at some of the graphs and we see these lines and we see these oscillations, we need to make sure that the oscillations are down to the very minimum, because otherwise the variations, the temperature, the pressure, or even the speed can change from one state to the other. And of course what we're looking for is a steady state. Now here we have a boiler system, very simple one. It's probably part of a turbine system. Now the output needs to be kept quite constant, so what we do is all the time it's being monitored, and the compressor here and the boiler is then turned up or down to keep this generator and keeping the output at a very stable state. So we have the various pressures of the pipes, of the heating systems and the condenser. So of course they have to be kept, the pressure keep constant. Temperature at every stage needs to be monitored. And of course airflow into the combustion chamber of the boilers. So there'll be quite a lot of sensors knocking around the system like this, or keeping an eye on things to make sure that we get this constant output from the turbine. Of course the turbine would run a speed. So of course we need to keep the speed constant. Of course that will of course in turn turn the generator, and the generator will then produce the power. More sophisticated systems, we have algorithms to look at the controller, and that will be programming the runs. The algorithms will be sent to the processor, and this is where we'll see this one in a block diagram soon. We are going to be looking at, we won't go into detail on the Boolean algebra side, but we were looking at a thing called this PID system. Now what I've decided to do is include just a basic piece of electronics within the feedback system, so it's quite easy to understand. Here we've got a very simple operation amplifier. We've got an output, we have the input here. This R2 is where we feed the input to, and this here where we're looking, which is going back from the output to the input. We call this RF, and this is the resistor which feeds back the signal. And depending on the ratio between these two here, this will depend on the output, but it will keep it a constant. But the thing about it is, if we change the input, of course the output will change, but the gain of it will remain the same. And this is going into the input side, because we've got the plus side over there, and we call that the positive feedback. And of course that the signal that we see on this input will be in phase with the signal which is on the output. So this is the effect of positive feedback within the system. So the gain will increase as long as the input to V is positive. When the input side V in comes negative, the gain will start to sort of fall and will decrease. Right, we're going to be looking at the negative feedback side. We're going to use a similar circuit, operation amplifier, and just want to explain a bit about the how the negative feedback will work in a system like this. So here we have a very basic op amp. I mean, when we look at stuff like this is not just the full concept of the control concepts, but this just gives you a basic understanding. So this time we have a signal which comes in. It could be a similar input signal, but instead of being fed into the what we call the non-inverting input, this is in the inverting side, because you've got the negative. Of course, we've got this RF, this feedback resistor feeding back here. And so when we put the signal in here, we'll be looking at we get the gain, but of course the output, the V output, will be not in phase with the input. It will be out of phase with it. So this is why we are connected up, and what will happen is that the signal that comes out of this V output compared to the input signal will be inverted. And also as well, we can also reduce, because it's going into the negative side, reduce the voltage, and this also will stabilize the gain of it. And these, depending on what type of equipment we're running at and how it's going to be fed, so we can use either the sort of a negative feedback or a positive feedback. And here's just the formula here, that if we want to work out what the gain of that circuit, that op amp circuit, is. Now what will happen is that when we do have, for both the positive and negative feedback, we reach a saturation point, where in other words we can't really allow the gain of the circuit to go up any larger. Now these are all in relationship to what we call the PID controller, which we're going to be looking at a bit later on. So let's look a bit more into these controllers, and we've got these diagrams here. Now with here we've got what's known as disturbance sensor. Now that could be something which could be affecting the actual temperature, so it may be controlling some form of boiler system, or it could be in another system where they have to keep the motors stable, that they don't actually speed up or slow down, and that we don't want any effect from any external things to create that problem. So this is a bit more of a complicated, more complex, a very interesting sort of block diagram here. So we've got here where we've got various feedbacks, and you can see here how these loop back to each other there, and we've got measurement sensors, and then of course you've got the set point, which will then decide if the input needs to be raised or lowered and things like that. And we can see the word computation here, so this is bringing in the electronics, algorithms and stuff like that. And this is a feed for a forward control system. And of course, throughout a system like this, we are measuring the external disturbances. Now, these external disturbances, which are something which are not really controlled by the system itself, these could be something to do with the actual heating system. It could be where the machine it's running, or the system running, has to run in a very stable, and the area mustn't have any form of physical vibrations. So they set the system up so that the actual bed of the system is running very, very stable. And this can vary all things, and there's various sensors that keep an eye on this, and they have to send it back to the set points, and decisions have to be made. So the compute side of it, we're looking at there where it says compute. This is where we get into the computerized of it to keep the system running. Of course, here we call this system is a block diagram. Now, when we're looking at system tuning, we have various algorithms. So, in other words, when we tune the system, the processor could already be pre-programmed, but then we have to do some various tweaks to get the system to run and working in the most effective way. Now here we're getting into here, and we're starting to see the more mathematics side of it. Now, I don't want to go into the more of that side of it. This is already predetermined, but what we do have is we have the integral side, we have the derivative side, and that is all calculated in the various points along the line and the various feedbacks, and they are already predetermined, pre-programmed, allows the operative just to change a couple of settings and the system will run fairly smoothly. And of course we have, this is the known as the interactive algorithms. So this is how the PID control will set up these algorithms, and they will vary from system to system depending on the manufacturers, and you can look at the manufacturer's data sheets to see how they're set up. Of course, the design engineers for this will have privy to this information and be able to use the calculations. And of course, with using now sophisticated software systems, it makes our life easier. Now, there's a lot of maths involved in using this for the PIDs, and what I've done is I decided I found a nice piece here based on here. So what we've got here is where we can see here in highlighted, it says the proportional integral derivative. As you can see here, it's a simple state of the PID controller keeps the output of a system constant. As simple as that, based on the user's provided set points. Here we go down into the second paragraph here, and the PID controller assists in the process by ensuring that the HVAC, because this is looking at heating, venting, air conditioning system, gets a desired set point temperature as efficiently as possible. So it's done quickly so that the system is set at the right temperature. And finally, we want to reduce the failure rate down to 0 or down to the minimum. This is because of the undue wear and tear of the mechanical components, because they don't work forever. You can use types of mechanisms and components which they're not pure, they will break down at some stage for the resistance, and of course this will be cost and the energy consumptions as these systems are not working effectively. So PID controllers, they were developed in the 19th, 20th century. They've been around for some time, but they've not been as formalised as they are today. And now with a lot of the systems that we use today, it's like the PLCs as well. They were really sort of coming into sort of active really until the 1970s really. because of the electronics, microelectronics, Silicon Valley, and then the types of components that we're using, and of course what has made these systems become into their own is the fact that we have a lot of computerized systems today, microelectronics, so these PID controllers now become in their own way. So let's look again at these PIDs, and we can see here this block diagram, and what we want to be able to do is just take you through it. So we've got the set point here, we've got this proportional, we've got the integral derivative, and these here are already predetermined with the program, mathematically based there. So at the end of the day, the output here is kept at a constant, and depending what we put as the input. But that's all done for us, and it's very cleverly the way it's all done. So we're just going to briefly look at each one of these. The integral tuning point informs about the duration of time, how long it's been, the difference between the set point and present system example. Because remember, when these systems are running, they're not running for a minute time, they're running for quite a period of time. So there will be some variation between what the signal variations and the actual time itself. So what we'll have here is that the integral part of it is that we'll be measuring and looking at how that in time-wise. Now this one here, the tuning parameter, which is a proportional called KP there, that is looking at the difference between the desired set point and the out point. So where we can see it, we're looking at the KP here, so this is where we're looking at the output with the set point here, and we've got the KP as well. So they're all different types of terminology for the PID to be controlled. And of course we want to minimize any errors in the system as well. We want to keep the speed, if it has to be changed up or down, that it actually happens very quickly. So the derivative, which you know is KD, that also again is this part of a system here, and that's another part of where it's being monitored, and that again, that's the rate of change between the set point and the present system output. So that's your set point there and the output, and of course it's measured into there, and of course that will be set. There'll be algorithms to work it all out. Of course, all put together should give us a nice steady output. Now, if we look at this table here, we can see what the parameters, and we can look at what the rise time and the overshoot setting times, steady rate, state error, and stability, and you can see how these all come into with each other. Now we have the Ziegler-Nichols open loop system, and this is looking at the set point process variable. You'll see this in most textbooks. What you're trying to do is reduce this oscillation effect down to the minimum. From where you can see the step point over here, and you want to see what's going on just to keep it down so it actually slows it right down. The Ziegler-Nichols is also known as a reaction curve, and here we have the mathematical side of it, which we can see here, and let's look at the rate of change and see how this reaches the PV, which is of course the process variable. You can see here we've got the set point, and you can see what's happening here to get this to be a fairly constant output. Now 0.63 is very similar to what we have in the charge of the capacitor, if any of you are doing the electronics. So here are the table for all this and the various formulas which will work out to do the algorithms. Of course, we're using this for the closed loop tuning. We want to keep the KC side here a very, very low value. And we can see here the difference between the 2 points here. We've got the set point here and the process variable as well. Now another method that's being used is a Cohen-Kuhn tuning. Very similar to the Ziegler-Nicholas open loop system, and this is how it's all used. So we can see there, look at the tables at the top here, this table here. And then we've got, again, this is lambda tuning. It's similar to the Ziegler-Nicholas open loop. And all various of each other, and depending on what sort of system you're running at will determine which system you're actually going to run. And this is showing you again the formulas that are already set up in these systems. What you want to try and do is keep the overshoot down, and this is just showing a diagram here, block diagram here, to show you what you need to do, and the flow diagram tells you where things have to change to eventually get from the input to the actual output of the finish. Thank you very much. Further reading you can look at the UniCourse study guide.